The universe is full of wonders. It's a vast expanse that stretches beyond our imagination, filled with countless stars, planets, and galaxies. Each twinkling star in the night sky holds secrets and mysteries that have fascinated humanity for centuries. It's a vast and mysterious place, filled with incredible phenomena that we are only beginning to understand. From the swirling clouds of gas in distant nebulae to the majestic spiral arms of galaxies, the universe is a treasure trove of wonders waiting to be discovered. One of the greatest mysteries of all is the origin of life itself. How did life begin? What were the conditions that allowed the first living organisms to emerge from the primordial soup of early Earth? How did life arise from the non-living? This question has intrigued scientists and philosophers for centuries. The early Earth was a hostile place, with volcanic eruptions, violent storms, and a turbulent atmosphere. Yet, somehow, life found a way to emerge and thrive. It's a question that has puzzled scientists and philosophers for centuries. Throughout history, many theories have been proposed, from the idea of a divine creator to the concept of spontaneous generation. But the true answer has remained elusive. Now, a team of scientists from Stanford University has made a groundbreaking discovery. Their research has shed new light on the origins of life and has the potential to revolutionize our understanding of this fundamental question. They have found evidence that the spark of life may have come from a surprising source: microlightning. This tiny but powerful phenomenon could have played a crucial role in the formation of the first living organisms. This isn't the massive lightning we see during a thunderstorm. Instead, microlightning occurs on a much smaller scale, within tiny water droplets. These droplets collide and break apart, creating electrical charges that can spark chemical reactions. Microlightning is a phenomenon that occurs when tiny water droplets collide and break apart, creating electrical charges. Imagine the early Earth. Volcanoes dot the landscape, spewing ash and lava into the air. The atmosphere is thick with gases, and the oceans churn with violent waves. The air is thick with gases. Oceans churn and crash. In this chaotic environment, microlightning could have provided the energy needed to create the building blocks of life. These tiny electrical sparks could have triggered the chemical reactions that led to the formation of amino acids, the building blocks of proteins. Within this chaotic yet fertile environment, microlightning could have provided the energy needed to create the building blocks of life. The early Earth was a dynamic and ever-changing place, with the constant interplay of volcanic activity, atmospheric gases, and oceanic turbulence creating the perfect conditions for life to emerge. This is a major breakthrough in our understanding of how life began on our planet. The discovery of microlightning as a potential catalyst for the origin of life opens up new avenues of research and exploration. It challenges our previous assumptions and encourages us to think differently about the conditions that could support life. This discovery opens up a whole new world of possibilities in the search for life beyond Earth. If microlightning could spark the formation of life on our planet, it raises the intriguing possibility that similar processes could occur on other planets and moons. It suggests that life could arise in a wider range of environments than we previously thought possible. From the icy moons of Jupiter and Saturn to the rocky surfaces of distant exoplanets, the potential for life exists in places we may have never considered before. This discovery not only deepens our understanding of our own origins, but also expands our horizons in the quest to find life elsewhere in the universe. Water is essential for life as we know it, but water is more than just a solvent. It's a dynamic force capable of generating electricity. This is the surprising power at the heart of microlightning. Picture a single droplet of water. Now imagine billions of these droplets tossed about by wind and waves. As these droplets collide and break apart, they create static electricity. This is similar to the static electricity we experience when we rub a balloon on our hair. The air crackles with energy. But instead of a giant spark, this energy is released in countless tiny bursts. These are the bolts of microlightning, minuscule yet powerful. They are invisible to our eyes but capable of transforming the very chemistry of the early Earth. This process, repeated countless times over millions of years, could have provided the spark that ignited life on our planet. The early Earth was a very different place, a world that would be almost unrecognizable to us today. It was a planet in its infancy, still forming and evolving, with a landscape dominated by volcanic activity and a sky filled with thick, swirling clouds of gas. The atmosphere was a toxic mix of gases, including methane, ammonia, and carbon dioxide. These gases were released in vast quantities by the numerous volcanic eruptions that were a common occurrence on the young Earth. There was little to no oxygen, making the air unbreathable by today's standards. The surface was barren, devoid of any visible signs of life, and covered in sulfur clouds that added to the hostile environment. This was a hostile environment, but it also contained the raw ingredients for life. The volcanic eruptions spewed out not just gases, but also minerals and other elements that would be crucial for the development of life. Think of it as a primordial soup, a bubbling cauldron of chemicals and elements, all mixing together in a chaotic dance. This soup was rich in the building blocks of life, but it needed something to bring these elements together in the right way. These gases, churned by volcanic eruptions and bombarded by ultraviolet radiation from the sun, created a chemical playground. The energy from the sun's rays and the heat from the volcanic activity provided the perfect conditions for chemical reactions to occur. But something was needed to organize these elements, to assemble them into the complex structures that would become life. The random mixing of chemicals was not enough. There needed to be a catalyst, something to drive the formation of more complex molecules. This is where microlightning comes in. These tiny electrical charges, generated by the friction of particles in the atmosphere, could have provided the necessary spark to kickstart the chemical reactions needed for life. These tiny electrical charges could have provided the energy needed to break apart the molecules of these gases and reassemble them into new and more complex forms. The lightning would have acted like a natural laboratory, breaking down simple molecules and allowing them to recombine in new ways. It's an elegant solution to a long-standing mystery. Scientists have long wondered how the complex molecules needed for life could have formed in the harsh conditions of early Earth. The idea that microlightning could have provided the necessary energy is a compelling one. The chaotic, energetic environment of early Earth, far from being a hindrance, might have been the key to life's emergence. The very conditions that made the early Earth so hostile could have also provided the perfect laboratory for the creation of life. The interplay of volcanic activity, atmospheric gases, and microlightning created a dynamic and ever-changing environment, one that was ripe for the emergence of life. The Stanford scientists didn't just theorize about microlightning. They took their curiosity and scientific rigor to the next level. They recreated the conditions of early Earth in their lab, meticulously setting up an environment that mimicked the primordial atmosphere. They combined the gases of the early atmosphere, such as methane, ammonia, and hydrogen, with water droplets, simulating the ancient oceans. And then, they subjected this mixture to micro-discharges of electricity, akin to the microlightning that would have been common on early Earth. The results were nothing short of astonishing. The experiment produced a range of organic molecules, including amino acids and nucleotides, which are the building blocks of life. These molecules are essential for the formation of proteins and nucleic acids, the very foundation of living organisms. Among these molecules was uracil, a crucial component in the structure of RNA. Uracil is one of the 4 bases that make up RNA, alongside adenine, cytosine, and guanine. RNA, or ribonucleic acid, is a close relative of DNA, deoxyribonucleic acid. While DNA holds the genetic blueprint for life, RNA plays a vital role in translating that blueprint into proteins. RNA is essential for all known forms of life, acting as a messenger and a catalyst in various biological processes. Imagine the excitement in the lab as scientists realized they had created one of the fundamental components of life itself. This was not just a theoretical breakthrough, it was a tangible step towards understanding the origins of life. The experiment demonstrated that microlightning could have played a crucial role in the emergence of life on Earth. These tiny electrical discharges could have sparked the chemical reactions necessary to form complex organic molecules. This finding gives us a tantalizing glimpse into the very origins of life. It suggests that the conditions on early Earth were ripe for the formation of life, with microlightning acting as a catalyst. It suggests that the transition from non-living to living might not be as miraculous as we once thought. Instead, it could have been a natural progression driven by the laws of physics and chemistry. Perhaps it was a natural consequence of the laws of physics and chemistry, playing out on a young and energetic planet. The interplay of these forces could have set the stage for the emergence of life. The young Earth was a dynamic and volatile place, with frequent storms and volcanic activity. These conditions, combined with the presence of microlightning, could have created the perfect environment for the formation of life. As scientists continue to analyze the data and refine their models, we move closer to understanding the complex processes that led to the emergence of life on our planet. The study of microlightning and its role in the origins of life is just one piece of the puzzle. Future research will undoubtedly uncover more about the fascinating journey from simple molecules to living organisms. This research not only deepens our understanding of Earth's history, but also has implications for the search for life beyond our planet. If microlightning could spark life on Earth, could similar processes be at work on other planets? The study of microlightning and organic molecules opens up exciting possibilities in the field of astrobiology. By understanding the conditions that led to life on Earth, we can better identify potential habitats for life elsewhere in the universe. The journey of discovery continues as scientists around the world collaborate and share their findings. Each new piece of evidence brings us closer to answering one of humanity's most profound questions: how did life begin? The story of life's origins is a testament to the power of scientific inquiry and the human spirit. It reminds us that even the most complex phenomena can be understood through careful observation, experimentation, and collaboration. As we look to the stars and ponder the universe, we are reminded that the quest to understand our origins is far from over. Each discovery brings new questions and new opportunities for exploration. The journey from non-living to living is a story of transformation, driven by the forces of nature. And as we continue to explore this journey, we gain a deeper appreciation for the intricate and wondrous